Today, we're going to continue our journey of multiple integrals by thinking about coordinates in R3. We're going to start thinking about coordinates in R3 by reminding ourselves about how coordinates work in R2. So, if you recall, we had two different types of coordinates in R2: rectangular coordinates and polar coordinates. Rectangular coordinates just had two distances. We had a length and a length. X was the length or the distance from the origin, horizontal distance from the origin to the point. Y was the vertical distance from the origin to the point. The thing to note here is that X and Y are both distance or both length. I'll say distance. It's a distance. And X is also a distance. We describe a location with two distances. In polar coordinates, we still need two coordinates because we are still in two-dimensional space. Whatever dimension space you're in, that's the number of coordinates you're going to need to uniquely describe locations. In polar coordinates, we had two distances. We had one distance, the distance from the origin, or in this case, the pole, and an angle. So the R is a distance, and theta is an angle. This exhausts our possibilities. We can't describe a unique location with two angles. We need some kind of distance to show up in what's going on. So in this case, we have two distances, or a distance and an angle. That's it. Every other description of R2, all those descriptions of R2, those different bases you found in R2 that weren't the standard base in linear algebra, those are all variations of this rectangular coordinates theme. If we define theta in some other way, we are still going to be using a distance and an angle. It's just going to be some variation on polar coordinates. All those bases in linear algebra are just some variation on rectangular coordinates. These are just the most convenient ones for us to do. I used the wrong color on R. Now it's going to look like I tried to do the problem in 3D. So there's no more room. We have to have at least one distance. We've got another one. It could be a distance or an angle. That's it. Let's talk about R3. When we describe R3, we have three different ways we can describe R3. And it's based on the number of angles that we're going to use, given the fact that at least one of our coordinates has to be a distance. So I can go distance, distance, distance. I can go distance, angle, distance. Or I can go distance, angle, angle. Now I'm out of possibilities. At least one of my coordinates has to represent some kind of distance. The other two we can describe with angles. So we got three coordinate systems to describe our R3. So we got three coordinate systems. we're going to have three coordinate systems for R3. Our possibilities are distance, distance, distance. Another possibility is to go distance, angle, distance. Or we can go distance, angle, angle. Three dimensions, three possibilities, because we have to have at least one distance. And then the other, it's either two angles, angle and distance, or two distances. One color short of making the color scheme work without using black, but oh well. If we're describing R3 with three distances, that is rectangular coordinates. There's an X, a Y, and a Z. This one we are familiar with. It's our favorites. So three distances is rectangular coordinates. The graph, not really paper, but the grid for rectangular coordinates is going to be a bunch of rectangles, specifically little cubes if we make X, Y, and Z all with the same unit vector. So we get rectangular boxes. The second one, where it's distance, angle, distance, specifically this order, this is cylindrical coordinates. Cylindrical coordinates are similar to rectangular coordinates, in fact, in that they use the same Z. We just describe the floor with polar coordinates and then put a Z-axis on top of it. So rectangular coordinates in R3, we use the same X and Y that we used in rectangular coordinates in R2. We just include a Z on top of that. Cylindrical coordinates are just polar coordinates on the floor. So R and theta. And we use the exact same Z that we would use in rectangular coordinates. So rectangular coordinates in R3 is a rectangular coordinate floor with a Z-axis. That's a distance. Cylindrical coordinates are just polar coordinate floor with a Z-axis. The third kind of coordinate, where we have one distance and two angles, that's different. These are called spherical coordinates. Where we have a distance, change up my color scheme, rho, and angle theta, that theta is the same as the theta from polar coordinates and cylindrical coordinates. And then we have this other angle, which is going to be phi. This one is actually different. Yeah, I'm not happy with this color scheme either, but we're just gonna have to run with it. Yeah, but I need more difference between R and rho, because I'm using the same theta. Yeah, I'm gonna go back to the original one. Oh. Because I'm worried about very important things, apparently. The names for these coordinate systems, rectangular, cylindrical, and spherical, are descriptions of what the graph paper would look like. I know paper is supposed to be flat, but imagine the grid. The grid for rectangular coordinates is a bunch of rectangles. The grid for cylindrical coordinates is a bunch of cylinders. Because we're just taking circles on the floor and adding height to it. If we just take the circle on the floor and add height, we're making cylinders. Spherical coordinates, we're having spheres of different radius coming from the origin. So we have one distance, how far are we to from the origin, and then two angles. So if we draw rectangular coordinates, we're just taking this rectangular floor with X and Y and adding height to it. So I've got some X coordinates. It's the X distance. Then I got some Y coordinates. And then I got some height on that. And so here I have coordinates X, Y, and Z. X, Y, Z. We just take that X and Y floor and we put a height on it. X, Y, and Z. Correct. For spherical coordinates, we wouldn't be able to say something like X equals R sine theta or X equals R cosine theta, because in spherical coordinates, there is no R. We would say, well, X is R cosine theta. Theta we have, but there is no R. So spherical coordinates look at R and say, well, what are you talking about with this R? Go ahead. Rho is distance from the origin, but it's not R is the distance on the floor from the origin. So R would be the distance my feet are from that corner. Rho would be the distance, say, if I want this point up here, the distance of this point to that corner. That's much farther than my feet are from the floor. So in cylindrical coordinates, I'm using just polar coordinates on the floor. So I would have this R. That's the distance R. And theta is measured from the positive x-axis. So now this location is theta R, and the height is measured with Z. So notice that R is not the distance to the point, it's the distance to the point on the floor underneath. So that's without the Z distance. So here's our rectangular and cylindrical coordinates. Now, if I want to describe that point, if I want to describe that point in spherical coordinates, I only have one distance from the origin to that point. That's the distance rho. So I'm not worried, I don't have this z. So r is a distance down on the floor out to this point. We still care about this point on the floor because that is still how we find theta. So that theta we still care about. So we do still care about this point sitting out here on the floor. But instead of using the distance from the origin to the point on the floor and then the distance going up to the point, rho is the distance from the origin to the point, and that's the only distance we're going to use. These are spherical. So that distance rho is from the origin to the point. The other angle that we're going to bring in, is from the positive z-axis down to the point through that plane. So I've got two angles. So if I want to locate that blue tape up on the ceiling from the origin, I need to know how far it is to that point. That's rho, from the down here in the corner up to that point. And then I need two angles. So first is measured from the positive x-axis. I turn towards that point. And then the second angle is going to be measured from the positive z-axis down to the point. That's where phi is going to go. Phi is measured from the positive z-axis. Theta is measured from the positive x-axis in the plane. So theta theta is measured from the positive x-axis, and theta is in the xy plane. That is the same angle that we have in polar coordinates to describe the floor. It's the same angle that we have in cylindrical coordinates to describe our angle. The other angle that we use in spherical coordinates is phi, and phi is measured from the positive z-axis. Phi is measured from the positive z-axis. Pause for copy. Notice that the angle phi is in the plane containing the z-axis rotated through an angle of theta from the positive x-axis. Theta is an angle in the xy plane. Phi is an angle in the plane cutting through the z-axis at an angle of theta. So we have relationships between rectangular and polar coordinates. For rectangular and cylindrical coordinates, those relationships hold. X and Y and R and theta is all stuff that's happening on the floor, so nothing changes there. If we have rectangular and cylindrical coordinates, X is R cosine theta, Y is R sine theta, and Z is just Z. X is R cosine theta, Y is R sine theta, and Z is just Z, because we're taking the same floor in rectangular or polar coordinates and just putting Z axis on it, the same Z axis on both. Spherical coordinates is different. And this point up here is rho theta and phi. We do have the same theta, but rho and phi are new. Here's what we want to grab to figure out a relationship between a connection between rho theta and phi and our old friends, rectangular and cylindrical coordinates. I want to grab this triangle up here. This should have been like a blue. It's same as R. I want to grab this plane that's coming out at an angle. I want to grab this plane that's coming out at an angle. That's been cut by this. Where this side, this distance is rho. Down here on the floor, we have an R. And in here, we have an angle. Everybody see where I got that rectangle from? This distance up here is the Z. Now we can make a relationship between the cylindrical coordinates and our spherical coordinates. If we have a relationship between cylindrical coordinates and spherical coordinates, we'll have a relationship between rectangular coordinates and spherical coordinates, because we have a relationship between rectangular and cylindrical. Now I'm highlighting rho, R, phi, and Z because theta is the same in cylindrical and in spherical. In both coordinate systems, we're using the same theta. So we don't have to draw theta in here, but it's right here. If I reorganize this to make it look more like a right triangle, to get a right triangle out of this, here is a right angle. So if I just grab that part where I have Z, here's R, and here's P. So now we can see a relationship between rho and R and Z and phi. Those are the only ones that we need because theta is the same in cylindrical and spherical coordinates. Rho is our hypotenuse, so R is equal to rho times the sine of phi. The theta is the same. The theta in cylindrical coordinates is the same as the theta in spherical coordinates. Z in cylindrical coordinates is going to be rho times the cosine. Once we have this relationship established, now that we have this relationship, we can say X is rho sine phi cosine theta, and Y is rho sine phi sine theta. So if I have spherical coordinates and I want rectangular coordinates, I get to reuse theta because theta is the same in cylindrical and spherical. Three different ways describing three-dimensional space. Question? How's everybody okay? Whatever dimension space we're trying to describe, that's the number of coordinates we need to describe it. One of those coordinates, at least one of those coordinates, has to be a distance. We have to know something about distance. Any questions? Rho would be x squared plus y squared plus b squared. Any other questions? Incorrect. There's another question. I said we could describe two-dimensional space with two angles, but we would have to have some form of distance. We would have to know how far apart those 2 points were. So distance does come into play. So those of you who remember doing constructions in geometry, one of the ways we could find a midpoint is between 2 points is we just do the compasses and then we make a perpendicular line, right? Everybody remember doing constructions in geometry? No one does constructions in geometry anymore. So did anybody do constructions in geometry? Where you get like a straight edge, not a ruler, just a straight edge. You can make a line and you can measure arcs, but that's it. How many people did constructions? I did. So it's really weird that someone your age did that in their geometry class. I want to find your geometry teacher and say, dude, really? That's pretty cool. Any questions? This is where you get things like you can't square a circle and you can't trisect an angle. Any questions? It's about picturing how we measure points. So if I wanted to locate where the projector is, and this is my origin, this wall, I know all this and that is like not really useful. So I have to animate this and make a hologram. I'll edit that in. So if this is our origin down here at this corner by the door, and this wall going from the front to the back of the classroom is the x-axis, and along the floor and this wall where the board is, that's the y-axis. Then the z-axis would be the corner from the corner of the floor to the corner of the ceiling. If I want the location of that projector, I would find my x-coordinate. Be right here. I'd have to walk through this desk to find my y-coordinate. Stand under the projector if I can't do it with the table. Go here, and then I'll need the distance from the floor up to the projector. That would be my z-coordinate. If I wanted to find the cylindrical coordinates of the projector, I'd start here in my my origin, and first I would do theta. I know we list that second, but it's more convenient to turn first. So I would start from the positive x-axis, turn to an angle of theta till I'm facing the camera. I would see how far I have to go on the floor to walk over there. Pause because I have to kind of go around this table. Walk to the point underneath the projector and then measure the height from the floor up to the projector. That's my z-coordinate. If I wanted to give the spherical coordinates of the projector, I wouldn't be able to walk there. I have to fly there, but I'm not allowed to fly in public. So you just have to imagine. I need the distance from the origin to the projector. So I need this distance, right? I need that distance. It's not something that I'm going to walk. I can't like go walk up that through the space. It's that's a distance to space. Then I would need theta, which is the same theta that I walked in my cylindrical coordinates. Then I would need phi. I would start off with this angle. My finger is pointing up at the ceiling and I'm standing in the corner still, but I've misbehaved. And then I would measure phi from the positive z-axis down to the projector. I really need to move my origin to shoulder height because I can't like be like lying on the floor and pointing at the projector. So that's how I would locate the coordinates of that projector in our 3 coordinate systems. Yeah. 1 distance, 2 angles. 2 distances, 1 angle, 3 distances. We are going to start using these in triple integrals. If you're wondering, it's like, oh, how come we never described things before? It's never really been an issue before. We could just get away with X, Y, and Z. It only becomes an issue now. That's why we're dealing with it now. So we have the additional issue of making a triple integral out of this. With 3 distances, dx, dy, dz, that's a dv. No problem. That's a little chunk of space. a dx, a dy, and a dz, a little rectangular chunk of space. We know how to make a dv in cylindrical coordinates. I have a dr, that's a little chunk on the floor, a dr, a d theta, that's not a distance, but we just need to multiply by r. And then I need a dz, that's a distance. So dv in cylindrical coordinates will be r d theta dr dz. For spherical coordinates, two of them are angles. I need two different arc lengths to turn those angles into distances. Right now, d rho is the only thing that's a distance. I need to turn d theta into a distance. I need to turn d phi into a distance. So that's the problem that we're going to be dealing with next week in triple integrals. Next time on Calc 3, angles must become distances. I don't know how to make it more dramatic. Well, we're going to make angles into distances by multiplying and using the arc length formula. It's just not dramatic. I need to get Kiefer Sutherland in here to say things really intensely and then, like, I don't know, beat someone up. Yeah, or I need Batman. Maybe Batman would make it more dramatic. Gravelly voice Batman. We'll go with gravelly. That's the most. Mostly because it's easier to do a gravelly voice than it is to do Adam West. Although that would be my smart thing. I like how all the actors have to be superheroes now. They're like on steroids, so they can have like muscular bodies and stuff like that. And Adam West was just like, oh, nah, I'm in good enough shape. Give me the spandex. And he was just rocking the spandex. Alright. I mean, he made millions of dollars, so it's billion. Oh, that is my favorite bat suit and Batmobile. All right, that's going to do it for today. That's going to do it for this week. I will see you all on Monday. Everybody have a good weekend, and thanks for playing.